Look at this, a universe of data, points scattered across space, some following a pattern, others wandering at random. There is something hidden inside this noise, a structure, a signal. This series is about giving you the mental tools to find it. We're building from the ground up, 4 parts, 28 chapters in total. I'll drop a new video every 2 to 3 days, so you'll always have something to come back to. Part 1, The Foundations, chapters 1 through 7. Part 2, Inference and Learning, chapters 8 through 14. Part 3, Evaluating and Improving Models, chapters 15 through 21. Part 4, Advanced Statistical Machine Learning, chapters 21 through 28, and we start right here, chapter 1. Why do machine learning engineers, people who use powerful algorithms and deep learning models, still need statistics? Somewhere out there is the truth. A real relationship, a genuine pattern. Maybe it's how blood pressure relates to age, or how a chip temperature predicts its failure rate. But when we go and measure the world, we don't get the truth. We get observations, messy, incomplete, full of random variation. Each measurement has uncertainty. Some sensors are imprecise. Some people don't answer surveys honestly. Some data just doesn't arrive. In machine learning, that can mean missing values, drifting sensors, or labels that are just a little wrong. Before a dataset exists, there is a process. Real-world measurement process, collected dataset. Some uncertainty is random variation, natural changes, noisy measurements, unpredictable events. Some uncertainty is systematic error, biased sensors, missing groups, or surveys that represent the wrong people. So can we ever recover the true signal from all of this noise? Yes. And that's exactly what statistics is for. If every dataset is a mixture of reality and imperfection, the next question is, how do we separate the useful pattern from the random mess? Here's a dataset, 70 observations. They look chaotic. But watch what happens when we apply even a simple statistical smoother. A pattern emerges. The underlying signal becomes visible. And these, the distances from the data to the smooth curve, these are the residuals. They are the noise. They never completely disappear. But now we understand them. A residual is simply observed minus fitted. But a residual is not always pure noise. Sometimes it is a clue. A pattern in the residuals can mean the model missed something important, a nonlinear relationship, an ignored feature, or a changing condition. Every machine learning model at its core is solving this equation. Data equals signal plus noise. In mathematical form, we often write it as y equals f of x plus epsilon. F of x is the signal. Epsilon is randomness, measurement error, missing factors, and uncertainty. Statistics gives us principled methods to separate one from the other. But even if we find a pattern in this dataset, one question remains. Does this data represent the whole world or only a small part of it? In practice, we almost never observe everything. The full population, all patients, all users, all sensor readings is too large, too expensive, too slow to measure entirely. So we take a sample, a small, hopefully representative slice, and from that slice, we make inferences about the whole. A sample is useful only when it reasonably reflects the population we want the model to work on. If a medical model is trained mostly on one age group, or a driving model only sees sunny weather, the sample can be large and still misleading. That is sampling bias. The data is real, but it represents the wrong world. The true population mean, we call it mu, is unknown, but our sample mean, x bar, is our best guess. And if we took another sample, x bar would move a little. Different samples give slightly different estimates, and statistics tells us how good that guess is. This bracket is a 95% confidence interval, a principled statement of uncertainty. A confidence interval gives a plausible range for the unknown population value based on the sample we observed. Every time you evaluate a machine learning model on test data, you are doing statistical inference. You're asking, does this sample performance reflect the true performance on future real-world cases? Here's a dataset. Each point is one observation. Some feature X, some outcome Y. Statistics finds the pattern, a relationship that summarizes how Y tends to change with X. This line is the model. Machine learning predictions come in different forms. Regression predicts a number, temperature, sales, energy use, vibration amplitude. Classification predicts a probability, failure or no failure, fraud or not fraud, disease or no disease. Both are asking the same statistical question: given X, what outcomes are likely for Y? We write that as P of Y given X, but we don't just draw a line, we wrap it in uncertainty. The inner shaded band is the confidence interval, the range of plausible average values at each X given what the data told us. For one new individual case, uncertainty is wider. That is the prediction interval. Now, a new data point arrives. Where will Y land? We can make a prediction, and we know exactly how confident to be. Suppose we train on 10 data points. Simple data set. There's a clear, gentle trend. In practice, machine learning usually gives data 3 jobs. Training data learns the pattern. Validation data helps choose model settings and complexity. Test data gives the final honest evaluation. A simple model captures it. It doesn't pass through every point perfectly, but it sees the underlying direction. It will generalize. Now watch what happens when we use a model complex enough to pass through every single training point exactly. It fits the training data perfectly. Training error 0, but on a new unseen point, the simple model predicts well. The complex model, complete failure. Training error looked perfect. Test error revealed a problem. There is another trap: data leakage. If future information or test information slips into training, the model can look brilliant in development and fail in reality. For example, predicting customer churn while accidentally using account close date as an input feature. It wasn't learning the signal, it was memorizing the noise. Statistics is what prevents this. Think of predictions as dart throws at a target. The bullseye is the true answer. High bias, all your darts clustered together, but far from the bullseye. Your model is consistently wrong. Underfitting, high variance, your darts are all over the place. Your model is inconsistent. It overfit the training data, both bad, scattered and off-center, the worst of both worlds. Ideal, darts clustered near the center, low bias, low variance. Another way to see this is model complexity. If the model is too simple, test error stays high because it misses the pattern. If it is too complex, training error keeps falling, but test error can rise again because the model memorizes noise. The expected prediction error can be decomposed into these 3 parts. Expected test error equals bias squared plus variance plus irreducible noise. Bias means the model tends to miss the true pattern in the same direction, even across many data sets. Variance means small changes in training data can produce very different models. More data, regularization, simpler models, and better features are all ways to manage this balance. Statistics gives us a framework to reason about these sources of error and choose the right level of complexity. Here is the ML pipeline as most people draw it. Data goes in, a model comes out, predictions follow, but the fuller story starts earlier and continues later. Real world, population, sample, data, model, evaluation, prediction, monitoring. But the critical layer, the one that makes the whole thing trustworthy, is this one: statistics. Statistics provides uncertainty quantification. It extracts signal from noise. It guides estimation. It tests generalization. It evaluates whether a model actually works. It gives us inference, the ability to reason from data to truth. Machine learning without statistics is pattern matching in the dark. With statistics, you understand not just what your model predicts, but why, how reliably, and when to trust it. Before trusting a model, ask, what population does this data represent? Is the pattern signal or random noise? How uncertain is the prediction? Does it generalize to unseen data? Has the real world changed since training? Statistics is how machines learn to think. In the next chapters, we will build the tools behind this thinking layer: data types, descriptive statistics, probability, distributions, uncertainty, and model evaluation. Thank you for watching. If this sparked something, subscribe. Stay curious, follow the maths, follow the data.